I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the 2025 FRQs from AP Physics 2. This is question 1 on version J. In this series of videos, we're going to talk about the AP Physics 2 FRQs from 2025. We're going to start with question 1 from version J. So question 1, we have two long current carrying wires, and they have the same current going in the same direction, where the wire 1 is on the x-axis at 0, and the wire 2 is at a distance of positive d. And both wires are in the xy plane, so they're parallel to each other. They both have the same current. And we're asked first to complete the following tasks in figures 2 and 3. And we want to use arrows or the symbols shown in the box to 1, indicate the direction of the magnetic field from wire 2 at point P, which is at the origin of the xy plane. And then we want to indicate the direction of the magnetic force that is exerted on wire 1 by wire 2 in our third figure. So the symbols that we're going to use is an X is into the page, or a dot is represents out of the page. So first we're going to start by doing the magnetic field from wire 2 at point P. So since wire 2 is a current carrying wire, what we're going to do is we're going to use the right hand grip rule, where we align our thumb in the direction of the current and we wrap our hand around the wire like so. And we can see that if we wrap our hand like this, that our fingers anywhere below wire 2 are going to be pointing into the page. Anywhere above wire 2 are going to be pointing out of the page. So that means anywhere below wire 2 has a magnetic field that is directed into the page. So we can draw an X to represent the magnetic field. So you probably only had to draw one X to represent the magnetic field, but I'm going to use multiple X's as it'll help us with a later problem. So the next question is asking about the magnetic force on wire 1 by wire 2. So we're going to treat wire 1 as just a single charge moving through a magnetic field. And we're going to use our force right-hand rule to figure out the direction of the magnetic force. So we're going to line hand like this. So we're going to line our thumb in the direction of the current, which is the charge that's moving. We're going to line our fingers with the direction of the magnetic field, which we know is into the page. And then we're going to recognize that our palm represents the force on a positive charge, which conventional current is the direction of positive charge moving. So our force is going to be upward. So we can just draw an upward arrow in the box to represent the magnetic force that's acting on wire 1. So this means when the currents are going in the same direction, that means that the wires are going to have an attractive force. We could do the same process to figure it out for wire 2, but we are only asked to do wire 1. The next question, part A2, tells us that we have a third current carrying wire that has twice the current and is in the positive x direction, so moving the same direction in the xy plane as the other two wires, and it's a distance of y3. Now, the key here is the net magnetic force exerted on wire 1 by the currents in wires 2 and 3 is 0. So in order for that to be 0, then if it has twice the current, we know that it's going to have to be a little bit further away. So we're going to draw it a little bit further away with twice the current. Now, it tells us to derive an expression. When you see the word derive, that means that you need to show all of your steps. And we're going to derive an expression for y3 just in terms of d. Now, when it says in terms of d, that doesn't mean we have to start with just d. We can use anything we want, but our final answer can only be in terms of d. So we're going to begin our derivation, as it says, by writing a fundamental physics principle or an equation from the reference information. So we're first going to start with, if we know that the magnetic force on wire 1 is 0, we're going to start by drawing a free body diagram for point P. So at point P, we know that wire 2 is attracting it, so we have a magnetic force from wire 2 pulling up on wire 1. Now, because wire 3 also has the current in the same direction, we know wire 3 is also going to be an attractive force, so it's going to pull downward. So the magnetic force from wire 3 is also downward. So then we're going to write our fundamental physics principle, which is the upward force is equal to the downward force. So the magnetic force from wire 2 is equal to the magnetic force from wire 3. Now we're going to use an equation from our reference sheet where we have a magnetic force acting on a current carrying wire is the current in the current carrying wire times the length of that wire, which is both wire 1, and then the magnetic field that's produced by wire 2, and that's going to equal the same current, same length, this time multiplied by the magnetic field from wire 3. Now you can see that the currents are going to cancel out because they're the same. It's wire 1, and the lengths would cancel out because it's the same wire. So that leaves us with the magnetic field of 2 equals the magnetic field of 3. So now we're going to go back to our reference tables, and we're going to find an equation for magnetic field on a current carrying wire. And the magnetic field produced by a current carrying wire is equal to mu naught times the current in the wire divided by 2 pi times the distance the magnetic field is away from that wire. So we're going to substitute that in for B2 and B3. And for B2, mu naught times I2, that's the current in wire 2, divided by 2 pi times D, which is the distance that wire 2 is away from point P or wire 1. And that's going to equal mu naught times I3, which is the current in wire 3, divided by 2 pi times its distance away, which is Y3. So you can see we have a bunch of constants here. Mu naught is going to cancel out. We're going to cancel out 2 pi, and that leaves us with I2 over D equals I3 over Y3. We can cross multiply to get Y3 times I2 equals I3 times D. Now we know that I2 is just I. It tells us that wire 2 carries a current of I, and that wire 3 carries a current of 2I. So now we can cancel out the i's, which leaves us with an equation of Y3 is equal to 2D. Now, because wire 3 is attracting wire 1 and wire 2 is attracting wire 1, we know that because the currents are in the same direction, in order to have a magnetic force that is 0, that the third wire has to be below the wire 1. So that means that the position is not just 2D, the position is negative 2D. The next part tells us that wire 3's move far away, which just means that it doesn't have a magnetic force anymore. And we're just looking at wires 1 and 2, and we have a circular conducting loop in the XY plane, and it's initially held at rest below wire 1. The loop is then moved at a constant speed in the negative y direction as shown here in this figure 4. So first thing that we need to do is indicate whether there's a clockwise induced current in the loop, a counterclockwise induced current, or there's no induced current. So what we have to do first is, before we're going to determine the clockwise, we have to figure out some things about the magnetic field that's going through this loop. So again, we're going to use the right-hand grip rule, and we're going to show that with the current carrying wire that anything below wire 1 has a magnetic field going into the page. Now remember that as the magnetic field moves further away from wire 1, it gets weaker. So we know that inside the loop, we have a magnetic field that's going into the page, and I represented a smaller magnetic field or a decreasing magnetic field as it gets further away by making the x's smaller. So the magnetic field in this case is directed into the page and is decreasing. So as that wire coil moves away from the wire 1, that means it's going to end up with a decreasing magnetic field as it goes through the wires. So with a decreasing magnetic field, that means that there's a change in flux that is occurring. So the magnetic field is directed into the page, and the change in flux that's into the page is decreasing. So that gives us a direction of change coming out of the page. Now, when the direction of change is out of the page, that means that our wire is going to produce a magnetic field and magnetic flux that points into the page. So the loop of wire produces a magnetic field that points into the page, which means now we can use our right-hand grip rule again to point our fingers and wrap around the loop to show that at the very top, the magnetic field that's produced by the loop shows a current moving to the right at the top, which means that the wire is going to have a current that is going clockwise. So You have to figure out the change in flux first. So with the flux going into the page in the loop with the wire, and it's decreasing with a decreasing flux coming into the page, that means you have a change coming out of the page, and the wire it produces that magnetic field going into the page. And then we can use our right hand grip rule to be able to explain why we have a clockwise current going through this loop. So this is free response question 1, version J on the 2025 AP Physics 2 exam. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.